Hello everyone, I'm Zhenyl, doctoral student from Zurich, Space Geodesy Group. And today, the title of my presentation is Assessment of Drone-based GNSS ZTDs for Data Assimilation and Weather Forecasting. So first we come to the motivation and background. In the past 2 decades, we already proved that GNSS meteorology has great power in the meteorology field. And a lot of studies is about simulating GNSS ZTDs, zenith delays, to improve the numerical weather models, predictions, and general weather prediction, especially for the community, the temperature, and even the precipitation. However, the zenith delays is the accumulated value which represent the troposphere information accumulated one above the ground point. So it cannot provide the profile information of the troposphere, but the profile information is quite crucial to the weather application and even climate research. But fortunately, we have the fast developing air platforms industry, like the unmanned aerial vehicles, UAV, and the drone. So we can use the drone to reach a different height to collect the data. And then we can get the profile data, and then get the profile troposphere information from data processing. So in general, it would be promising to assimilate those drone-based data to further improve the NWPs. And to support this research, first we need to know if after assimilation of this drone data, we can get improvement for the NWPs themselves. So already done research, as shown in this figure, it shows the relative humidity arrow, profile arrow for different cases. And you can see the black line is the case without any assimilation, and the blue line is with simulation of only ground-based stations, ZTDs, and the red one further assimilate the drone-based ZTDs. And we can see the significant improvements for humidity arrow, especially for the lower part of the troposphere. And based on that, in this contribution, we further to do the weather forecasting with these updated NWPs and to see their performance. And I'll come to the experiment. And I have to mention that it's a case study. So the drone data was provided by the Meteorologists AG in Switzerland. And the experiment time was last year, March. And the data collection lasts for just 60 minutes with the 1 second suction rate. And the GNSS data processed in RTK mode with the Assimilating software. And as you can see in the red figure, the drone flies ascend about 2,000 meters in this short period. So we have profile data there. And as for the weather application, we use the WOF 4.3 to generate the weather forecasting, and use the integrated data simulating system and the ZD operator in the Assimilation. And we use the GNSS forecast products to force the forecasting. And we have 2 domains, and the inner domain has a high resolution 2 kilometers, and the drone fly in the inner point, the inner domain. And now it's the framework of the study. We first did a 6-hour forecasting to add the spin-up process to make the model into balance. And then we simulate the GNSS ZTDs after this 6-hour forecasting, and then make another 3-hour forecasting based on the updated analysis. And we designed 5 cases in total. And as shown in the table, and the case control means we don't assimilate any ZTDs, and case all means assimilate all available GNSS ZTDs, and the case partial means we assimilate 1 in every 10, that is a tenth of observations. We also designed another 2 cases, low and high, which means we assimilate only ZD with height below or above a certain height. Here is 1,200 meters. And as you can see in the figure, it shows the height changes with the time. So basically, at the beginning, the drone was on the ground. It seems like the ground stations, and then it's set. And now we come to the result part. First, let's see together how assimilation will affect the humidity and temperature field. And as shown, these 2 figures show the water vapor mixing rate changes and temperature changes after assimilation. And the inner point is the flight point, and we can see after assimilation the humidity generally decreases while the temperature increase for this case. And we also see the most significant changes happen around the flying point. And also the effect will decrease with the increasing distance from the flight point. And we also need to do the validation. And here we have meteorology sensors mounted on this drone to measure the humidity and also temperature for forecasting times and showing the figure. So we can evaluate their performance at least 4 times. And first is about the evaluation about the humidity. And the left 4 figures shows the humidity arrow profile for 5 cases at these 4 times. And you can, as you can see, the blue line shows the case without assimilation, and the red line is with assimilating of all the available observations, and other 3 cases in other 3 lines. And we can just see a decrease of humidity arrow at the lower part of troposphere. And the red figure shows their statistics for 5 cases. And then we can see if we assimilate all available GNSS ZTDs, we can have the smallest humidity arrow. And the prediction improved by 30% compared to the case without any assimilation. And we also have found that the other 2 cases, the low and high, these 2 cases are worse than the case control, which means maybe if we only assimilate observation, maybe make the case worse. And now come to the result for temperature. And still the figures are similar. And we can still see the improvement after assimilating drone data. And the temperature prediction improved by about 9% compared to the case control. And also the largest improvements happen at the lower part of the troposphere. And still the case low and high are worse than the case control. And we also want to know how long the assimilation effect will last. So we implemented another 12 hours forecasting for case control and for the case R, which is the best case study. And we use the RMS of the difference between these 2 cases as the assimilating effects. And here, these 2 figures shows the assimilating effects change, how the effects will change in time for humidity and temperature. And first we can see the effect generally decreased with time, which is reasonable, because we just assimilated at 1 time point. And we also found that for humidity, the effect can stably last for about 10 hours. And for temperature, it decreased faster, but still can hold for 3 hours, so maybe enough for short forecasting. And now we come to the conclusions again. So for both humidity and temperature, assimilating drone-based GNSS will help, but only when they cover a wide range of altitudes, the whole profile. If we only assimilate a part of the observations, like below or above a certain height, maybe make the case worse. I can also find the assimilation effect decreases with time, but also can support the short-term forecasting for like 3 hours. But I have to mention again that it's a case study. So in the future, the first thing is we want to have more drone-based data, and then we can implement more experiments. And especially if we want some sequence drone-based data, then we can carry out the cycling weather forecasting, which is more like in practice. And that's all for my presentation. Thanks for your attention.